All right, everybody, we had a couple of days off with snow on Wednesday and then the guest speaker on Friday. And we do have a test coming up after the Easter break. And I know some of the homework is beyond what we got to on Monday. So I wanted to give you, I'm going to try and make shorter videos so you can digest them in a little quicker time. Just cover a couple of topics instead of trying to do too much. So today, in this one, I want to just give you a little bit of information about motors and generators, which are pretty big concepts in our modern society, electric motors and electric generators. First, we'll work with motors because it's something you're more familiar with. And we're going to try and show, I've tried to make a 3D diagram here that can help you understand a little bit more about what's going on. So let me go to the program that I want to use for the moment. And the simple explanation here is that these blue bars that you see are supposed to just be wires, okay? And I've only shown one wire loop. In a motor or a generator, there are thousands and thousands and thousands of these, but I'm just showing one to give you the principle. So this is just supposed to be a wire loop. This bar in the middle, this gray bar in the middle, is an axle, and the wire rotates on that axle. So let me see if I can show you what I mean by that rotation. The wire can rotate on that axle. All right, this is a characteristic of motors and generators that wire loops rotate. So I want you to get the idea that this wire loop can spin. All right, and as you can see, this red arrow coming through here is the B field. That's the magnetic field. Now, what I don't show you are the magnets. There are magnets inside of motors and generators that create this B field, but that gets a little bit too cluttered if I try to show you the magnets. But again, just imagine that we have a north pole over here on the right, and the B field is coming out of the north pole. And we have a south pole over here on the left, and the B field is going into the south pole. And we know that's the way B fields go. And so we have this B field, this red B field here, and we have this wire, okay? And now what you have to imagine is that I can hook up a battery to this wire. And I'm going to hook up a battery in a particular way, and I'm going to make current flow through this wire, and we're going to see what happens by using our right-hand rule. And the point that I want to make for you is that when we talk about current, see the letter I over here, current, I. When we talk about electric circuits, we talk about current flowing. But in terms of the right-hand rule, it's QV. And what I wanted you to be aware of is that the current has a certain direction. It flows through a wire, along a wire. That's the direction of QV. Current is positive charges moving, and so QV is positive charges moving with a velocity v. So in terms of the right-hand rule, when you see I, you should think that's the direction of QV. And you push your four fingers of your right hand in the direction of QV. So let me change programs now so I can draw a little bit more. Here's that same diagram, only now it's not dynamic, it's static. Let's put our a couple of vectors on here. So let's do this. Let's say that I hook up a battery so that current is going to flow in the direction of these green vectors. Current's going to flow around. And so all of that is current. So that's I. And as we just said before, that's also QV. So over here I'm going to say QV. So on the right-hand portion of the wire loop, the current is flowing into the page. And on the left-hand side of the loop, the current is flowing out of the page. And since the current has different directions, I'm going to have to do two right-hand rules. One right-hand rule for the right side, one right-hand rule for the left side. And over here on this back piece of wire, we don't even think about that because there the QV is parallel to B. And we know that for a magnetic force to exist, the QV and the B have to be perpendicular. So we ignore that particular piece of QV. It's unimportant. Only this QV here and this QV here are going to produce a magnetic force. And the question is, what's the direction of the force, and what does that do to our system? So let's just use our right-hand rule. If you point your four right-hand fingers in this direction along into the page, okay, and then you point your palm in the direction of the B field, which would be this way, you should find that your right-hand thumb is pointing up. So there is a, let's put this here. So F magnetic is up. I know it looks like the same direction as the green current. This is where you have to remember this is a three-dimensional perspective. So what I'm saying is, if I do it like this a little bit more, the current is flowing in this direction into the wire, into the board, but the B field or the force is going to be up. Okay. And if the force is up, that force is not along the wire. It's perpendicular to the wire. So when a magnetic force on a charge, when a force on a charge is pushing it in the direction of the wire, then the charge just moves easily along the wire and we get current. But when a force is pushing a charge perpendicular to a wire, it actually pushes the wire. You got to imagine there are Avogadro's number of electrons or charges on this wire, and they're all being pushed up. That's going to give the wire, the entire wire is going to have a force up applied to it. The charges can't come off the wire, so they're going to push the entire wire in the direction of the magnetic force. And if we do our right-hand rule, you'll find that on this side, the magnetic force is down. And if that's the case, let's go back to our dynamic drawing. If the right-hand one is being forced up and the left-hand one is being forced down, hopefully you can see, and the thing is free to spin on the axle, this wire loop is going to spin. We've created a motor. We put current in on the wires, and the fact that there's a magnetic field oriented in the way that we show here means that the wire loops develop forces like we just figured out with the right-hand rule, and the wire loop is going to spin on the axle. And that's what an electric motor does. An electric motor takes current and changes it into mechanical motion. So I get a spinning wire, and what that does is that spins the axle, and if I attach a pulley to the axle can do work for me. Like spinning the platter on a hard drive, like spinning your washing machine, like spinning your dryer, like making a fan motor spin. If I want some kind of circular motion, I can get it out of this kind of a device, and this is a motor. So let's just summarize again real quick. When I start with current and get mechanical rotation, I have a motor, an electric motor. And it all comes from this QV cross B. F magnetic equals QV cross product B, there's that cross product, that right-hand rule. It's that idea that makes electric motors work. Okay? Now, let's talk. I promised to make this short, so there's an electric motor. Let's talk about this now in terms of something else. Instead of putting current into a motor, I'm not going to put current into the motor, into the wire. Instead, I'm going to put a crank on the axle. I'm going to put a hand crank on the axle. And I'm going to turn the hand crank. I'm going to grab the crank and I'm going to grab the handle and I'm going to rotate that. And when I rotate that, it's going to force the wire loop to spin. Okay, the wire loop will spin because I have a crank attached to the axle, and that's going to make the axle rotate, and the wire loop is attached to the axle and it will spin. So I'm starting with mechanical rotation. I'm grabbing the crank and turning the crank. And imagine that the crank is back here attached to this axle. And this is like a hand crank generator. You see in the old World War II movies where they had the field radio and they had to energize it. They would have one guy turning the cranks on a field generator while somebody else worked the radio. This is the same kind of an idea. You can buy emergency radios these days that have a little crank on the side. You turn the crank and you can power the radio even if you don't have any batteries. So here's the principle. So let's see how this works in terms of our right-hand rule, okay? So let's go back to our static drawing so I can draw on this a little bit. So a moment ago, I was showing you that I was turning the crank up. So this is V is up. The wire where the Q's are located are going up. So on the right-hand wire, QV is up. Now I know it looks like this should be the same as going along the wire, but this is not. This is up. Right? Just like when we had this up here, this is up. This is into the page. This is down. This is out of the page. Okay, and it's a perspective drawing, so you just have to keep that clear. Okay, so what I'm saying is this. When I say up, I mean up. I mean like this, and down is like this. So when I spin this wire, see how the right-hand wire loop is moving up and the left-hand wire loop is moving down. Okay? And that's the way I'm spinning the crank on that's attached to the axle. All right? So that's what I mean by up and down. So let's go back to this drawing. So there's a QV on this side. This is down. And I'm saying it's QV because the charges are on the wire, and the wire is moving in a certain direction, so the charges move with it. So I've got my QV. Let's do the right-hand side. Let's do this side over here on the right. I point my fingers out of the page, okay, up. That'll be out of the page. All right. Let's see, out of the page. No, that won't be out of the page. I'm sorry. That'll just be up. The wires are going in and out of the page. This is just up. So point your fingers up, and then your palm should be pointing in the direction of the B field, and you'll get your thumb pointing out of the page. And out of the page is the direction of the wire. So there will be a force on the charges in this direction on the right-hand side. This is F magnetic. F magnetic is out of the board, out of the page on the right-hand side. F magnetic. That's the charges on that right-hand wire will feel a force pushing them along the wire out of the page, coming out over right here, okay, coming out of the wire on this side. When I say out of the page, I'm looking at it now. Okay, remember, this wire is going up, and when it goes up in this magnetic field, there's going to be a force trying to make charges come out the end of this wire, out of the page. Conversely, on this side, I have my QV is down. Point your right hand fingers down. The B field is pointing to the left. And if I do that correctly, I'm going to see that I get a force into the page. This is F magnetic. Kill that. Let's see. F magnetic is into the page here, and that's along the wire loop. Okay, so as I move this, as I rotate this, the force on the charge is going to want to make charge come out this wire and go in this wire over here, into the page and out of the page. And if I've got both sides of the wire having charge like that, the charge in the middle is going to have to go this way, right? And what I've created now, if the force on the charges that are on the wire force those charges to move along the wire, then I've created electric current. When charges move along a wire, that's electric current. And so here's the principle of a generator. When I start with mechanical rotation, and end with electric current, I have a generator. This is the primary principle of our modern society. We have electricity because of this principle. Electric utility companies have big turbines that have steam blowing across the turbine blades to spin an axle that has a bunch of wires attached to it. And as those wires spin in a magnetic field, they have big magnets that produce a magnetic field. That creates current flow on the wires, and then they sell that to you and me as electric current, as power for us to use. So there you go. There are two quick examples of a motor and a generator, all of it understood now, hopefully with the aid of the right-hand rule, which is what you really want to be learning. And the important thing is for you to get this geometry correct so that you understand the geometry of this, okay? All right, hope that's helpful. I'll post a few more of these. There are a couple other examples of the right-hand rule that I want you to do. But just take this for the moment and digest this. Thanks.